Hello, this is Dr. Brothers, and I am going to be going over lecture number 16 today for ECE 3058, Computer Architecture. This is concurrency, number 1, talking about threading. So here's what we're going to go over in this lecture. What is concurrency? From a software point of view and from a hardware point of view. From a software point of view, we're going to look at it with regards to programs, processes, threads, instructions, and data. From a hardware point of view, multiprocessor, simultaneous multi-threading, ILP, SIMD. So the different hardware configurations that support threading. So let's first go over the software. Program. This is the static image loaded into the memory. So we oftentimes talk about in the past we've talked about the caching and the RAM, the page table. These are associated with a single program. So each program will have, excuse me, each program will have a certain set of registers and a certain set of the memory space. Process, a program in a state of execution. So the process is going to be the program plus all the state registers, the page table, all that surrounding peripheral that go together, that makes up the process. So this evolves. So think about the page table. You might start off with a single entry in the page table, and that would consist of the program is the data in the page table, and the page table itself is going to be part of the process that's running. Then as the program uses more memory, there might be more pages allocated to that. So the current state of a given process evolves as time moves forward. Now a thread is the way that a program is broken down into states of execution. So we're going to take the processing language that needs to actually be performed and break it up into the threads. And so now we can put these threads on multiple processors, and those in summation are going to make the program. That gets down to the final state, which are the instructions, individual steps within a thread. So this goes all the way back to laboratory number 1, laboratory number 2, and this is dealing with the load word, the add, the multiply commands that are actually executed on the CPU. Everything ties back to that basic starting point where even the most complex program is broken down into instructions. So how do we make sure to protect each of these processes? Because on a computer system, as it's running, there are multiple processes. So we don't want them to interact with each other. We want them to stay in their own memory space, so there's no corruption, or there's no situation where a program is created to intentionally be malicious. If it is such, we want to keep it contained as much as possible. So we have multiple processes. Each process could have one thread or multiple threads. And then we also have the system process that is assigning what these do. So software threads, as we can see in this last slide, there's a whole bunch of different software threads. These are spawned by the OS and maintained by the OS. On a given computer, you might say have 4 cores, the ability to run 4 simultaneous threads. But in software world, you might have a whole lot more than just 4. You might have hundreds of threads. And then the operating system is going to go through and determine which threads get access to a CPU at a given point in time. So there is a difference between a software thread and a hardware thread. Software can be suspended in a state of software by storing the registers, storing the memory to the side. A hardware thread is limited by the hardware that can actually run a given thread. And that's what we have here. Number of software threads that can concurrently run on a given piece of hardware. So these appear as different cores to the OS. And as we go through this, we might see that a core could be a CPU. It could be a CPU has actually multiple cores where a CPU could be replicated. Or it might be hyper-threaded, which would still appear as different cores, but there's limitations to hyper-threading. We'll see that in the coming lectures. So why do we want to do multi-threading? One of the reasons that we want to do multi-threading, it allows multiple applications to run simultaneously. Back in the dark days of computers, they could only run one thing at a time. And so if the operating system was running, the operating system was the only thing that was running. Once you booted up a program, it would put the operating system on hold and it would run the given program. So to evolve beyond that, they came up with this idea of threads. And so it's a way of abstracting away. We've talked a lot about abstraction this semester. It's a way of abstracting away, making things more modular. So we also get to a situation where threading enables us to not rely so much on what the OS specific does, but it gets to this idea that we can distribute it across multiple platforms even. So we're no longer constricted even to a single computer. We might even do this as a cloud computing infrastructure where there are a whole bunch of different CPU systems, a whole bunch of different computer systems that can all be utilized to solve one process. Yep. So let's look at this. We can have some, let me turn this into a pointer real quick. Pointer, I want a laser pointer. Okay, we can have some compute operation that's going on in this thread. And then there's some IO interrupt that comes in, and so the thread has to wait for the given IO. Maybe it's retrieving data, maybe it's storing data, maybe it's an input from a user. And then the IO result is needed to finish this bottom compute thread. So we have the top compute thread that's going, and then it has to stop and wait for a while, and then it will continue going. So in this manner, this is a sequential process where we're going to do the computation, then we're going to wait for the data, and then we're going to continue to do the computation. There's another way we could do this, where we have this compute thread, and instead of just saying, okay, we're going to go and wait and go, we could say we need this IO, but we don't need it until this point in time where the arrow is actually pointing at. So we can say up here that we're going to spawn another thread to go and get it, and then this thread can continue. And then when it needs the actual data, the data is ready for it and it can pull it in. This is the idea behind a multi-threaded application where you can spawn threads to go and do things, and then it joins back together and you can run parallel to run faster. So the same way we were talking about in the computer architecture, doing pipelining, the idea is that we would have multiple operations running simultaneously. In pipelining, we were talking about the fetch, decode, execute, memory write-back stages. And as something was being first fetched, and then as it's being decoded, the next item is fetched. This is working in the same way. It's going to go ahead and go and fetch whatever information it needs to have it ready when this compute thread needs it. Obviously, this is a little bit more complicated, but compilers are extremely good at figuring a lot of this stuff out. So let's think about this webcam thing. We talked about this just a little bit in class, where I had a webcam at the back of the room that was presenting the information to the online audience. And the way that it works, you have a webcam, it goes through some digitizer, it goes through some, let's say, a tracking, and then this one is going to go through an alarm stage. You know, they're basically saying this one is a home security system, but you can put any series of computations in the chain that you want to. In the classroom, we were collecting data, we were sending it to the computer, we were then broadcasting the data out. So the same thing, it's multiple stages that are happening in order to take something and get it to the end user. Okay, so each one of these could be conceptualized as a different thread. So as we have multiple threads, we have to have a way to control those multiple threads. So here is a dispatcher model where we have a request queue. So there are a series of threads that are waiting in the queue, and then they are sent to a dispatcher. And the dispatcher is going to look at the CPU cores that are available. So this is how the operating system looks at the world. And when there is a CPU available, the dispatcher will take from the request queue and put it into one of the workers. The thread that was running there, say a thread needed to there was an interrupt that came up and the interrupt needed to be serviced. And so it would stop the thread and it would store that state so it could return later. Or you could have a team model where the request queue directly has certain CPU cores. This works well if it is a priority based. So you might have each one of these cores is for a different priority thread. So maybe we have the system thread's highest priority. You have a thread to handle data or a core to handle data requests, ... on down the line. So given different priorities, it doesn't need a dispatcher, where in this case, all the workers are of equal value. These members of the request queue, they're each going to have a different priority, and they will service threads that priority. We could also do something like a request queue with different stages. So this is shown like a pipeline model, where as one of these comes to a stall, everybody can move down and keep pushing it through. Now, this model A is the most commonly used model. This is how Windows does it. It has a queue of threads. It has a machine that's going to watch all the cores, understand the strengths of each one of these worker cores, and be able to dispatch threads to the appropriate levels. These other ones, not really used. So let's consider threads as a programming abstraction. What we want to do is be able to dynamically create threads, communicate amongst threads, synchronize activities of threads, and then terminate threads. So if you think about a standard program, it's going to accomplish some work. It's going to communicate that work, because if it's only doing that work and it's not sending that work out to anybody, there's no reason to do the work. So the communication might be amongst the display, it might be amongst the disk drive, it's communicating that somehow. And then it's synchronizing activity. So you might have to have input from the user, you might have to have file input, somehow it is going to be synchronized amongst multiple threads. If we go back to the webcam example, these are all doing handoffs as it's going down. So these handoffs have to be synchronized. It has to know when the digitizer is done with a set of data, the tracker can take it, and once the tracker is done, this alarm system is then going to process the tracked data. So you have to be able to pass it down the line in a synchronous manner. And then once everything's done, you have to be able to terminate a thread, release the hardware assets in a elegant manner. So a lot of times, threads will die, and if you're not doing good programming practices and a thread dies, it is left for the OS to then go and do trash collection on it, and it might not be able to really discern whether the thread is actually dead or whether it's just waiting. So you have to have really good programming practices when you're dealing with threads, that you terminate them when you're done with them. For this class, we're going to use the pthreads library in C. So here's how we do it. Creation, pthread create, top level procedure and arguments, and then communication, rendezvous, can create a wait state for children, and then you can join it back. Synchronization, we have mutex and then conditional variables. We'll go through an example of mutexing. Then termination, you return from the top level procedure, and then you explicitly kill the threads. This is what I was talking about. Make sure you do your own trash collection. You don't want to leave these things hanging around for the operating system to have to determine whether it should or should not get rid of these resources. Thread creation. A thread executes some portion of a program. So you have a program as a whole, it's going to get broken up into little jobs. Each job can be given to a thread. So it has an entry point, it has an exit point, and then it has to communicate some data. When a thread is created, this is the entry point. It's usually got an address from some function. So some function is going to spawn the thread, and that'll be the parent. So you have a main thread, and it's going through. And here's the spawning function. And it's going to create thread foo with arguments. And so once this is created, we get a new thread, and it starts to run. Once this thread terminates, it returns back into the main. The main thread is the one that needs to take care of everything, such as killing off all the children. So int foo, return 0, int main. We have it doing some stuff right here, but we have a child thread, and here's where the child is getting created. And then we're going to join back at the end. We're going to join back into the main thread. So that's like coming back into the main. So a thread automatically terminates when it exits the top level procedure that it started. Additional libraries may be provided for an explicit call for terminating a thread in the same process. For instance, terminate thread. If you do this, you might have a thread that you don't know when it's finished, and it might need to be killed off, and so you can terminate it. So a thread wouldn't be very useful if it couldn't communicate the results of its work. So when we have sharing of data, what we need to do is be able to use software to accomplish moving data around. If we think about this from a CPU perspective, that means that the data needs to be in the same page table. So we have multiple CPUs now that need to access the same page of memory. So the way it works, we might have CPU A, we might have CPU B. They're both running the same program, but different threads. And then as they go through, they will join at some point, either in a higher level of cache, so the shared cache, or in the page table. They'll join up to the same page. All right. Data race is a condition where multiple concurrent threads are simultaneously trying to write to access a shared variable. So like I said, we're going to have multiple CPUs. Those are going to go through multiple layers of cache. And then at some point, they're going to join together in order to have the same variable stored in memory. So given that statement, you are guaranteed to have the same variable in 2 different cache. And maybe that same variable will be stored in 2 different registers on the 2 different CPUs that are running it. So you are 100% guaranteed to replicate a variable. So we have to have a means of communication between these 2 CPUs to know who has the variable at a given time. And if you don't have control of said variable, you cannot write to it. So that is the programmer's responsibility to make sure that's done. If you don't, you get what's called a data race. And you don't know which value is going to be written back to the memory because it depends on how fast the CPU is. And if there's an interrupt that happens to that CPU, there's no way to tell which one will finish first and actually write the data back to said variable. So in order to do that, what we have to do, here's an example. If we have 4 threads, all of them are going to do count plus plus, and then print count. What will print, we have no idea. So here's an example of how these might spawn off at different times, given the how busy your CPUs are. So what we need to do is have everything either in a sequential program where you're only dealing with one variable in one thread at a time, and then you return from that thread and then pass that to another one. Or you do parallel programming. This is the more common approach. It's also more complicated. If you can do a sequential programming where basically you'll have buffers between each stage, and you write into the buffer, and once the buffer is full, you let the next thread know that the buffer is full and it can take it, and then this thread goes away and the next thread takes it. But parallel execution means that you're going to have multiple writing to the same variable at the same time. You have no way to know which thread will actually write to it first, and so what you have to do is mutex at variable. So higher level language statements, not atomic, more on this later, meaning this is 100% up to the programmer to make sure if you're doing parallel execution, if you have multiple CPUs that can access the same variable at the same time, you have to determine who will get it first. Okay, so here is the synchronous behavior. This is what I was saying. First, you have a thread that's going to produce some data. You have a buffer sitting in the middle of it. Then you have a consumer. So it is going to go A, B, and then C. Okay, so let's look at an example. So let's say that we have this shared buffer. This is going to be, we're going to create this structure. We're going to have some producer, consumer, and there's going to be a buffer in the middle. So here is the frame buffer. This is a FIFO. It has a head and a tail, and then it has a variable called buff available. Buff available are the number of available positions in this buffer. So if we are looking at 100 from 0, let me turn this into a laser pointer. So from 0 up to 99, so we have 100 available buffer slots. Buff available would start out at 100, and then it would decrement every time a frame was put into here. So we're checking the available spaces. So we're going to start out with the digitizer. Every time it has a frame to put in the frame buffer, it's going to decrement the number of available slots in the buffer. Every time the tracker pulls one off, it's going to increment the available slots in the buffer. So we're going to be looking at how much space is left in the buffer. So here is a section of code that shows how we're going to start off initiating all of this stuff. We're going to start off with an unsigned max size of 8 in it. We're going to have some function prototypes, digitizer, tracker, and then safe condition variables. We're going to use a Boolean, predictable, and a mutex for the condition of the buffers that are going to be shared between threads, the variables that are going to be shared between threads. We're going to make in this way so that they are thread safe. So buff lock is going to be a variable that's going to exist, and it is going to be a pthread mutex initializer. Excuse me, I can't speak. So here's where we enter into the main. Pthread, thread 1, and thread 2, and then we're going to create these threads with the digitizer and the tracker, and then we're going to wait until all of their processing is completed, and then we're going to join them back together. This will destroy them at the end. So here's our first example of what we're going to do. Here's the functions inside the digitizer and the tracker. We're going to have this buff available, and it's going to be decremented each time the digitizer puts an image in the frame buffer, and then we're going to have the tracker, and it's going to increment the buff available every time it pulls something out of the buffer. So theoretically, this should all work as long as we don't ever get a race condition between these two. But we're not locking these off. There's no way to tell, given this function or given this function, which thread is using it at a single time. So here's what could happen. We might have two different processors running this code. And what could happen, we want to start off with buffer available 5, and it starts off and that loads down to two different CPUs. So here's CPU A, here's CPU B. They're both going to be running these threads. So we have a distributed process. So there's going to be two different versions of buff available in the two different CPUs in their two different registers. Okay, so first thing, the blue CPU increments it by 1, and so the register 1 on the blue CPU is set to 6. Register 2 is going to decrement it by 1. Register 2 on the purple CPU is going to be set to 4 because we're not locking this off. So this is the race condition. Then register 1 is going to put it up into the memory device, store it back. So buff available is going to be stored back as 6. And then CPU 2, the purple CPU, is going to store register 2 back. So buff available would be set to 4. But if we look at this, what we want to happen, we incremented it once, we decremented it once. So what we want to happen is the final value, we want it to be 5. Neither one of these are correct. And that's because we are not doing thread safe processing on these variables. This is a problem. So what we want to do is mutex lock it. And we need to identify the critical sections of code. This is the code that is going to share variables between multiple processors. And then when we find those critical sections, we're going to make a mutual exclusion or a mutex. The way we do that is we're going to create a lock and then lock it or unlock it. Only one thread at a time can have the mutex. So this is the way that we can make sure that a variable is not going to be creating a race condition. So here's what it might look like. We might have 4 total threads that are running. Thread number 1 is in the critical section of code. Thread number 2 is approaching the critical section of code. Thread number 3 is past the critical section of code. Thread number 4 gets to the critical section, but because thread 1 has it mutex locked, thread 4 now has to stop and wait. It needs to stall until it can go into that critical section of code because T1 is going to release it, and then T4 can go into that critical section of code. So here's an example of how this might work. We might start off with identifying the critical sections of code. Let's say that we identify this, and now we've put a mutex lock and a mutex unlock. We can see a critical section of code on the tracker, mutex lock, mutex unlock. Is this functionally correct? Will this now work? Yes, it will work because we are locking this variable. However, is this good for performance? If another thread approaches this critical section and it's currently locked, this thread has to block until the mutex lock is released. And so for this one, we have a bunch of stuff in here that doesn't really concern the mutex locked variable, such as grab digital image. So it's too coarse. This is not going to be efficient code. These are the items that don't need to be here. So let's try again. Let's try again and restructure our code. So now what we're doing is while buff available is equal to 0, we're going to do nothing, but then we're going to apply the buff lock here and unlock it immediately right here after this is released. Okay, so now we've completely minimized what's going to be in this region. And we can see that we've applied another lock down here where we say, okay, so we're going to check it to see if it's 0, and we're going to check it to see if it's when we update it. And those two regions, that's it. That's all we're going to lock it for. And we're going to do the same thing on the tracker side. So only in the regions of the code where we play with buff available are we going to lock it. So how does this one look? Definitely a lot less the critical code that's in there. But now we've actually created a problem. we are locking it on a read. This again is bad because once it's locked, no other code can get into here. So while buff available is equal to 0, do nothing. This creates an infinite loop locked in here if it is 0 because it's locked. So if it's locked and it's 0, we are going to infinitely sit here because it cannot enter into this block of code. It's going to stall here. And so now we've created a situation where it is going to lock ourselves out of performance, and these will create a situation where we have deadlock. Both these threads will not be able to complete because they're both going to be stuck in critical sections. Same thing given this lock with the -1 and this check to see if it's at a max. It can get deadlocked at either one of these places. So again, this is bad. This does not work. So we need to be very careful when we go through threading. Deadlocks. There are two threads that are trying to get into the same variable. One is checking it, one is trying to write to it, and it can deadlock, and there's no way it can get out of that infinite loop. So be very careful of that. So let's try to fix our code again. So we're going to go through now, and we're not going to mutex lock it for a read because we don't need to. When we start doing mutex locks, it is now understood by the compiler that when a mutex lock is released, that variable will have been changed. And it will then have microcode written in MIPS in order to push that through and refresh that variable across the CPUs, and it'll indicate that that variable is stale, and it will reload that variable. Okay? So now we do not mutex lock it on read, but we do mutex lock it when we're only going to write this. So now we put the image in the buffer, we grab the image, we put it in the buffer, we increment the tail, and then and only then do we grab the mutex lock, change the number of available buffers, and then release it back into the wild. Okay, we have now really minimized the amount of time that it's going to sit here. Is this functionally correct? Yes, this is good now. How about the performance? So now we still have a problem because even though we've minimized the amount of time that it's going to have to stop and wait, we still have the problem that it could have to stop and wait. So is there a way we could make it even better? Because this works, this is good, but could we make it even better? Here are some more variables. So we have conditional wait, conditional signal, broadcast. We can use these now because this is a method of polling. And just as we talked about with the I/O, polling is basically the CPU saying, hey, are you ready? Hey, are you ready? Hey, are you ready? Hey, are you ready? We don't want to do polling. We just want to go along in this process, and then if it's blocked, we could change context, go to another thing, and be alerted when it's ready for us. And then we could, via an interrupt, we could come back to that thread knowing that our variable, that critical section is now open, and we could go back and access it. That's what these do. So block for a signal, and conditional broadcast. These are ways that threads can interrupt each other to where when there is a blocking condition, it can get this conditional signal sent to know that it can resume, and it doesn't have to sit there and poll it and actually use CPU cycles for that while statement. The CPU can go off and do something else, and it will just wait, and then it'll get this interrupt signal. So now let's say that instead of having a while loop for buff available is equal to 0, now let's put a conditional wait here. So thread buff lock, we're now going to buff lock it. If buff available is equal to 0, we're going to do a conditional wait, and then we're going to unlock the buff lock, okay, once it releases this thread conditional wait. So this is a blocking statement, but it's not actively spending CPU cycles here. How about this one? Functionally correct? Yes. Performance, concurrency, plus no busy waiting. So in doing this, we've gotten rid of these while loops where it was doing polling to see. And now we have the ability to, instead of sitting here just burning cycles on a while loop, we are going to have it inform us when it's ready. And here are the ways that these can be implemented. pthread conditional variable, we're going to have a not full and a not empty, and we're going to initialize these, and then they will be able to be passed back and forth, just like that. So, summary of the thread functions. We can create a thread, we can terminate a thread, we can mutex lock a thread, we can try lock, where the calling on this one, it returns a success if it gets the mylock, failure if it's currently used by another thread. So we can try to lock it instead of calling if locked. Mutex unlock, this is the way we unlock it. So the try lock, mutex thread lock, if this doesn't work, it will fail. And so the try lock is very much, these are very similar. Calling blocks, if it locks in the current use by some other thread. Failure, the lock is currently used by some other thread. Success, it gets the thread lock. So very similar on the try lock and the lock. And then unlock. Join puts it back together and it terminates the threads. Make sure you get rid of your threads. Thread conditional wait, this is going to look for that buff not empty, buff lock type signals. Thread conditional signal, buff not empty. This is the one that wakes it up. All right, kinds of threads. We already know that we have user level threads. These are used for an application, OS independent. Scheduler is part of the runtime system, so that's part of the OS. Thread switch is cheap. So all we have to do for these user level, we save the PC, we save the registers and the SP, the state registers, and that's all we have to do to switch because we can keep the same cache space. Right, we can keep all the variables because we're in the same application. So we don't have to switch out the memory space. So blocking called by thread blocking processes. Kernel level, expensive thread switches. This is because it has to switch all the context, including the memory. So it can't keep the cache. It has to flush out the cache and replace it with the kernel cache. So this makes sense for blocking calls by threads in this sense because at the kernel level, it is expensive to get in there. So once we get in there, we're going to block things and stay there. The kernel, the system, kernel is another word for the system. Kernel becomes complicated process for thread scheduling. Thread packages become non-portable. So kernel level, these have a higher degree of access. This is when the operating system takes over a CPU, and then it's more expensive to switch back out of it. So we already talked about this slide earlier. OS support for process and threads. So you can imagine that at a given process, it's going to have some number of threads. It's going to have some code that goes with it, some data, and then the process control blocks, the PC, the stack pointer, all of the things that go along with that given application that run in the background that we don't really see. The operating system controls them. So we might have processes that only have the master thread. We might have processes that have a whole bunch of threads. And then what we're going to do with these, we also have kernel processes. These are the ones who manage the user processes. So in the software layer, we might only have 4 CPUs. But if you count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 threads in this simple example. all 14 cannot run simultaneously. If we only have 4 CPUs, we can only run 4 different threads. And this is assuming that each one of these CPUs is an individual core. These are single cores. So each core can only run 1 thread. We'll get into multi-cores in just a little bit. Could be two-way multi-threaded CPU, that's what I'm saying. These might run more, but we could imagine that these are single-threaded or multi-threaded, but there is a hard limit on the number of hardware threads that we can run at a time. So, thread scheduling, this is lab number 5. How do you determine which of these software threads gets which core at what time? All right, so this is it for the introduction to concurrency. We will continue on next week when I return. Thank you for joining me for this virtual lecture on concurrency.